turn on the YouTube stream. So now it should be on. And there's a long delay between turning on the YouTube stream and okay, I'll just type here because Julian's probably just watching the YouTube. Okay, there we go. All right, so this is an extra tool. It might take a little bit of time. Let me look at my own YouTube. Yeah, it should be on right now because I'm seeing stream being live on the YouTube side now. And on Discord, it should be working as well. So Martin, are you still not seeing anything? Oh, okay. All right, cool. All right, so Martin may need to do the same thing to close in. Okay, great. Okay, excellent. Okay, so what we'll do today is basically just try to figure out how to move data between RAM and the registers. Okay, so there we go. All right, so let me just kind of quickly go over which part is RAM. So RAM is right here. Okay, this is the RAM component, and we want to be able to move things between the RAM component, locate the values of locations in RAM, and registers. So the registers, when I say registers, I'm talking about registers inside the register bank. So I'm referring to registers A, B, C, and D, because those are the only 4 registers that software or your code has direct access to. The other registers, they are around, but your software has no direct access to those registers. They can influence the registers. Certain instructions can influence other registers, such as the program counter here or the flags register over here, but not directly. Okay, but these 4 registers, we can manipulate the values of those 4 registers directly. We also want to be able to store values of the registers inside the register bank to the RAM component that I just pointed out over here. So today's focus is really just moving stuff around, okay? And then tomorrow we'll talk about how to actually perform operations like add, subtract, and whatnot. And the reason why we have to do it in this particular order is because everything that the ALU, which is this component over here, that can process, they all have to come from the 4 registers that I just talked about, registers A, B, C, and D, that resides within the register bank component itself. All right, so where do we get started? I mean, this is going to be a pretty big topic, is where do we get started? So instead of starting with the ROM component, which is down here, we'll just go ahead and figure out, how do we draw a path between the components that we need to connect. Okay, so the first thing that we want to do is let's try to do a store operation. Okay, so when you do a store operation, the only way you can store the content of a register to a certain location in RAM is to utilize up to 2 registers. One register will tell the processor where we're supposed to store that content, and then the second register will indicate the actual content to store. Okay, so I'll write on the side, okay, and hopefully you can see this too. So let me see if I can do something here. There we go, and then I move this over here. So this is kind of a little posty thing that I can kind of use to kind of track what I need to do. And you can see it has a little bit of transparency, because sometimes you want to see kind of what is behind it. So what we want to do right now is to say some operation like this. Okay, whatever register B, I just randomly pick one of the 4 registers, is going to get whatever content that register, let's say C, has. So this is the operation that I want to perform in the processor. Now I have to figure out how do I configure the pathways in order to make this happen. Does everybody understand what I mean by star b equals c? That's that's a notation borrowed from C and C++. I'm dereferencing b so that whatever b is treated like an address in RAM, and then I'm storing whatever register C has at that location. Okay, I'm not seeing any questions. All right, so this is what we want to do. So now the question is, I need to use RAM in this case, okay? Because if the whole operation says I need to store some content in RAM, and Catherine is typing, so I'm gonna wait until I see the question before continuing. And if you guys want to use the voice channel, that's fine too, because that might be a little bit faster. So does that mean we are storing the content of C in not in register B, but in the location that register B is pointing to? Okay, so let's make this more concrete. Okay, so I'm going to go here and make it more concrete. So let's just say that at this point C has the content. Now I use double equal here intentionally because I want to establish that this is what register C has right now. Okay, so let's just say the register C has 6E in hexadecimal, and register B has, I don't know, let's try C7, as the current content of register B. So when we perform this particular operation here, what ends up as the actual finished operation is whatever is at location C7 will be updated to a new value of 6E in hexadecimal. So that's basically the bottom line deal of what we are trying to accomplish. Okay. So are we doing okay so far with what we have been talking about at this point? Because that's just C notation. I'm borrowing the C notation to help me explain what we are about to do. And this is also why CISP310 is a really important prerequisite to this class, because we need to use the concept of pointers, addresses, and also dereference. So, but we are not using structures yet. Okay, so we are kind of just using the address of a particular byte in this case. Okay, Catherine is typing. So, okay. All right, so I'm putting that on the side because I want to go to the register bank, and I can show you this. You can do as well. Is you inject specific content into a register. Make sure that you're using the poking tool or the poke tool, and point to the register that you want to change, the value that you want to change. So register B is supposed to have C7. Just type C7 on the keyboard when the red rectangle is around the hexadecimal digits, and in register C is supposed to get 6E, so I just typed over that. So what I have just done is I am forcing the process. I'm injecting specific values into these registers at this point. So now I can go back to main, now that I have quote-unquote initialized the registers. And in main, you can see that there are 4 output pins that can also display the current content of the 4 registers. So that comes in pretty handy, because then we don't have to go into the register bank just to see that. All right, so if this is the operation that we want to perform, I'm putting this over here, and let me resize this so that it doesn't need to take up as much space, and I can make this always on top. So this way, even when I click on the Logisim window, this the little notepad thing will still be here, because we want to keep track of what we are trying to do. All right, so if you are utilizing RAM, okay, then you have a whole bunch of questions to ask, because when you're using RAM, then you got to ask the following questions. Okay, I'm typing it over here. So you got to ask the question of what is going to be the A port. Okay, where is it supposed to connect to? What is supposed to connect to the D port? RAM cell. Okay, so all of these tunnels connected to the RAM component, they need to be determined. Okay, so the clock one is not as important because we know the clock is going to go up and down, 0 and 1 and 0 and 1 all the time. So we have RAM load, and reset is not important because we definitely don't want reset to be a 1 when the processor is quote unquote operating normally. Let's see, what else do we need? No, those are the 4 ones. Okay, those are the 4 questions. So we want the A port of RAM, okay, to connect to. So I'm using this symbol. It's not an equal sign. It is establishing. We're saying that we want these 2 components to be connected eventually. So we want port A of RAM to connect to register B in this case, and we want the D port to connect to register C in this case. And we want RAM cell to be a 1. Okay, this needs to be a 1, and we want RAM load to be a 0 because that's how we specify a write operation. So how we use the select pin of RAM and how we use the load pin of RAM, we talked about that last Thursday. So I'm not going to repeat that, okay, because I'm assuming that you guys had time to review the content from last week, and hopefully also have time to kind of experiment and play with the components like I did on last Thursday. So I'm assuming that that's done already. So I'm not going to get into the details. All right. So in this picture, okay, you can see how RAM load is a tunnel, but that tunnel is coming from ROM here somewhere. Okay, so RAM load, you can highlight a particular node like so, and you can see it will highlight the same node no matter where it is in the circuit, even though it is connected by tunnels. So this is really handy because it shows you how you can track what the pin is. So I cannot change RAM load from a 1 to a 0 because it's tied into the output of ROM at this point, and the current value of the location that the ROM has selected doesn't have RAM load being a 0. But I'm just saying what we need to do. Okay, RAM select also needs to be a 1 because unless RAM cell is a 1, the RAM component is not selected. In other words, it's not paying attention whatsoever to anything. But these two are relatively easy. Okay, RAM cell and RAM load, they're fairly easy to determine because it's either 1 or 0, and if you know how the RAM component operates, which I'm assuming at this point is that you do understand how the RAM component operates, then it's not a big deal. Okay, these two are pretty easy to determine. But the more difficult ones are, how do we connect the A port of RAM to register B in the register bank, and how do we connect the D port of RAM? Okay, so this is not just D, this is the D port of RAM, and how do we connect that to register C in the register bank? So now we need to do some detective work. Now the detective work, if you do it in Logisim, is relatively easy because we can just kind of poke a wire and highlight it, and this way it's easier for us to track down where it connects to. So let's just take care of this first. Okay, we'll take care of how to connect register B in the register bank to A port of RAM. So this is A port of RAM. We click on this wire and it goes to a multiplexer. A multiplexer has multiple input and one single output, which means, okay, now we need to decide which input of this multiplexer should connect to that particular output. And so we need to track down these two. One goes to the program counter register. That doesn't seem like register B because register B is inside the register bank. So we try the other one. Okay, so you can see how this one connects to a demultiplexer. A demultiplexer is the opposite of a multiplexer where we have one in and multiple out. But the bottom line is, yes, if we configure the multiplexer here and the demultiplexer over here correctly, we can in fact connect the A port of RAM to the output one of the register bank. Okay, so let's make some notes here. So in order for that to happen, I need this input to connect to the output of this particular multiplexer, which means address mux needs to be a 0 because this is input 0 and this is the only output. So we need to specify the select of this multiplexer to be 0. So then we jot down some notes over here. So we say ADDR mux needs to be a 0. Okay, then we follow that that particular node over here, and we see that we have to configure this demultiplexer to also be 0 because the output that we want the input to connect to is output 0. All right, so we'll take some notes over here. We say register output 1 demultiplexer. The select of that demultiplexer needs to be a 0. Okay, so that will connect this particular wire coming out of the register bank to this. So now we need to look into the register bank and ask, how do we get register B to connect to output 1 of the register bank? So we right click on the register bank, then we say view register bank. So now we say, okay, this is register output 1, which is equivalent to the pin that or the port that we were looking at. So we now look at this wire and we ask, how do we connect this wire to this wire to this wire over here? And we can see that, oh, that should not be too hard because this wire connects to this wire through just a multiplexer. So now we look at this multiplexer over here and we say, this is input 0, this is input 1, and this is input 2. So we want input 2 of this multiplexer to connect to the output pin of register output 1. So that means we need to configure register output 1 select to be 2. So and that thing has a different name in the main circuit. So in the main circuit, the select of register output 1 is a lot shorter because otherwise I won't have enough room to type the name of a tunnel. So we want register output 1 select to be 2. So we now say register output 1 select needs to be a 2. All right. So now we have configured the processor circuit so that register C, excuse me, register B, right? Okay, I might have made a mistake here. I think we need register B. Okay, so I was incorrect. Register output 1 select should be a 1 because 0 selects register A, 1 selects register B, 2 selects register C, and then 3 selects register D. So I stand corrected here. I was incorrect. Register output 1 select should be a 1. And when I was explaining inside the register bank, I was clicking on the wrong output. I should be clicking this output and ask how do we connect this particular output from register B to this particular output pin of register output 1. So the answer is we want this particular input, which is input 1 and not input 2, as I said a little bit earlier. So I corrected myself. So are we okay so far? Are there any questions? I'm gonna give you guys a few seconds to ask questions. And looks like we are still good. All right. All right, so then what we need to do now is to look at the other port of RAM, because we said, okay, right here, we said that we want to connect register C in the register bank to the D port of RAM. So now we are looking at this particular node over here, and this node goes to quite a few places. Okay, so if you look at the diagram, it highlights a whole bunch of places, but of all the places, this seems to be the only one that I should be interested in, either that or this one. Because if you look at this particular way of connecting to a demultiplexer, we are having one output of the register bank to connect to the D port. But if you look at this one over here, then we're looking at one of the inputs into the register bank to connect to the D port. So now we have a choice. Okay, so we have to now choose between, do we want an output of the register bank to connect to the D port, or do we want an input into the register bank to connect to the D port of RAM. So the question now is, who is driving this node? Who is specifying the content of this node? And the answer is, because this is a write operation, because we are changing the content of a location in RAM, so it's a write operation as far as the RAM is concerned. And as a result of that, we need to have an output from the register bank to connect to the D port, because it is the content of one of the registers to specify the D port of RAM and not the other way around. So that means this is the connection that we want, which also means now we need to configure this particular demultiplexer. So when we look at this particular demultiplexer, it has got two inputs. The first thing is register output 0 enable needs to be a 1, because this particular demultiplexer, unlike the other demultiplexers, actually has an enable pin, which means if the enable pin is a 0, then none of the output is connected to the input. So we want it to be enabled first. Once it is enabled, it is output 2 that needs to connect to the input. So we need the demultiplexer, the selection. So register output 0 demux. So the select of the demultiplexer needs to specify a 2. So are we still doing okay so far? Is everybody still following along, how I set up, all of these various values? Mostly, okay. So the idea is there are a lot of details involved, okay? But the idea is you just track down, the connection between the components that we need. And in between, we usually just have a whole bunch of multiplexers and demultiplexers along the way. So if you think about this in terms of railroad tracks, okay, so now you need a train to go from a particular city to another city. So you just have to configure the switches along the way to route the train from the source, from where it starts off, to the destination. And it's the same thing with the processor, okay? Because multiplexers and demultiplexers are basically just railroad switches, with the exception that they are one-way only. Okay, all right. So assuming this is okay, then we go into the register bank, because this connection terminates as to one of the ports of the register bank. So now we look into the register bank, and register output 0 is corresponding to this particular pin over here. So now we're looking at this wire, and we're now asking, how do we get this wire to connect to this wire over here? So once again, they're only separated by a multiplexer. This time we really have input 2 to connect to the output. So to configure this multiplexer correctly, now we need to set up register output 0 select to be a 2. So we specify here register output 0 select is 2. Now this 2 and this 2 here, they're configuring different things. This one is configuring a demultiplexer that is outside of the register bank, and this 2 is configuring a multiplexer that is inside the register bank. So they're serving two different purposes. All right. So if all of the things are connected this way, then we're all set, okay? Which means we have register C to connect to the D port, and then we have register B to connect to the A port of RAM, and then combined with RAM cell being a 1 and RAM load being a 0, then the next rising edge of the clock will actually overwrite whatever location the register B is pointing to, which is C7, with the content that register C, which is 6E, that the register C is specifying. All right. So this is the store instruction. Okay, this is what the store instruction does. So yeah, okay, I'm gonna wait for Catherine's typing because I think she has a question. Okay, so the question is, where does register output 0 connect to? It connects to out 0. because I don't have enough space, on the packaging of the register bank to type the entire thing. So the reg part of all the names of the output pins and input pins are dropped on the outside because I just don't have enough room to do that. But to answer a more general question is, how do we figure it out? We go to the register bank, and it probably won't show here. Okay, so to answer that question, we open the register bank as a separate file, which I had done earlier today just when I was playing with it. So when you open up the register bank as its own, file in Logisim, then you can switch to the appearance mode, like so. And in this mode, you can click on a pin, right click, I think. You can, nope, you can just regular click. So you can just regular or left click a pin, and it will use a picture-in-picture to show you where it is located in the actual circuitry. So this is how you can figure out, how the output pins inside a design correspond to the port from the perspective of the appearance. Is that okay? So for the most part, I think in all cases, I preserve the order. So if you look at these pins, this is the top, this is the middle, and this is the bottom of the top of the circuitry. They correspond in the packaging in the same order, like these three over here. The top four, which goes from left to right, they also correspond to these four going from left to right, which looks more like from top to bottom, but same idea. All right, so continuing with the discussion here. So now the question is, well, the whole idea. So if this is not a von Neumann architecture, then these wiring will have to be done manually. Okay, you have to kind of reconnect a whole bunch of wires just to get this to happen. But since this is a von Neumann architecture, we can now specify an opcode, okay, in order to specify this particular operation. That is why the opcode table is really useful. So what we'll do is now we'll take a look at the opcode table. Okay, there we go. And I'll move this one to this side because I need to look at the content of the opcode table. So when you look at the opcode table and you look at column C, which is the C notation, is telling you what that opcode does. So you look for something that looks like what we saw earlier, and we see this line here. Okay, we see this row which has the same notation, star y equals x. Okay, and the other way to look at this is to look at RAM as an array and use y as an index, and then x is specifying the new content at that particular element. I personally prefer the first way, which is star y equals to x, dereference y, and store the value of x to the location that y is pointing to. So my preference is the first one, but if you want to look at RAM as an array, I suppose you can do it too, and that would be the second notation. All right, so when you look at this, okay, we did this lab last Thursday too. So when you look at this particular row, this is called the mnemonic. Okay, column B is called the mnemonic, which is basically just a slightly more symbolic way to represent the operation. Is store. Okay, when you see parentheses around a register, it means we are dereferencing, and that's really just the syntax. So in this case, we are storing x register. Whatever x is specifying has to be a register. We are storing the content of that register to whatever y is pointing to, and the parentheses once again is really just decoration, as far as we are concerned, to make it easy to see that we are dereferencing register y. And when you look at this particular bit pattern in column A, that is how we specify the opcode. Okay, the operation code, in short, opcode. So the opcode starts with 1111, and that's constant. You cannot change the most significant 4 bits of that opcode. But the other 4 bits, from bit 0 to bit 3, they specify which register is register X and which register is register Y. So in this case, we want Y to be register B, and we want X to be register C. So if you scroll all the way to the top of this particular spreadsheet, it shows you that register A has a bit pattern of 0, 0. Register B, which is what we want as Y, has a bit pattern of 0, 1. And then register C, which is also what we want, but for register X, has a bit pattern of 1, 0. No, to answer Sakil's question, these opcodes are not standard for most processors. And in fact, how we map the opcode, is it defines what we call the binary compatibility between processors. So if two processors, even if the inside is entirely different, but they recognize the same opcode to mean exactly the same thing, then those two processors are called binary compatible, which means that they're opcode compatible. This toy processor is completely an invention just for instruction purposes, so it's not shared with any other processor. Okay. All right. So onward. Okay. So now we want to look at the opcode. Okay. So we want to look at the mnemonic first. So mnemonics. Okay. So the mnemonic of the operation that we want is ST, which is really just the really abbreviated version of store. And we want register Y to be B, because register B is the one that is pointing to the RAM location to be updated. And then we want the other register to be C, because C is the one that is supplying data to update in RAM. So the opcode of this is going to be 1111. So the first 4 bits, which is specified over here, cannot be changed. Okay, that's fixed. However, register X is register C in this case, which is specified by the bit pattern of 10, and then register Y, which is register B in the specific mnemonic that we are dealing with here, is register B, and register B has a bit pattern of 0, 1. So we can see how this 0, 1 is corresponding to YY, because register B is corresponding to the placeholder of Y. And we can also see how register X is 10, because register X, or the placeholder X, is register C in this case, and register C is specified by a bit pattern of 10. So are we doing okay so far here, as far as knowing what is the mnemonic versus what is the opcode? So we got the mnemonic being SD in parentheses B, comma C, and then the opcode, okay, typo over here, and then with the opcode being 1111 1001. So do we have any questions about how I looked up the opcode table, found the mnemonic, and also figure out the opcode? Okay, I'm not seeing any questions. Cool. All right. So if you have to do this for every single instruction in a complex program, and when I say complex, for this class, the RAM only has 256 locations. So the worst we can do is 256 instructions. And some instructions take up 2 bytes too, so we are not going to have entirely 256 instructions. But it's still a chore to have to do this for every single instruction. So that's what the assembler is for. Okay, so the assembler is a tool so that you can type in the mnemonic and it translates it to the corresponding opcode. So the assembler is a very useful, handy tool, but in very short programs, we should be able to do this by hand. It's very tedious. I don't want to do it myself, but it is possible. So just to illustrate what I meant by that, okay, we'll go to the assembler. And make sure that when you want to specify the source code, you have to go to the source tab over here. And I'll just type it in, okay? Normally, you want to type the code in an editor and then just copy and paste it into the assembler. But in this case, it is a single opcode, so I can just do a just type it over here. So I want to store to whatever B is pointing to, and we are copying from register C. So that's my opcode. And then we wait for the magic of the assembler to happen, and it's done. And then also remember, if you want to get the file to download, and specify in RAM, it is the RAM file. Okay, so there are two components that you have to kind of distinguish. Those two are really important. One is the source tab. That's where you copy and paste the source code into, and then the RAM file is the tab that you want to be selecting while you download as a CSV file, so that you can specify that as the content of RAM when you update RAM content. Okay, so the bottom line is, we can see, it is exactly F9. Now, why is F9 so important? Because this particular opcode here, the bit pattern that you're seeing inside my little post-it over here, 1111 corresponds to the hexadecimal digit of F. 1001 is corresponding to the hexadecimal digit of 9. So I did hand assembled the mnemonic correctly to be the opcode of F9. Are we still doing okay so far? Any questions? Okay. All right, so David is, oh, better now. Okay, that's good. I guess it's compared to last Thursday or earlier today. All right, so what we'll do now is, because now we got two pieces, okay? We got, okay, so now we got all of this stuff here, okay? All of this stuff here, and then we got this stuff over here, and they are disconnected, okay? What does F9, the bit pattern of 1111, 1001, what does that have anything to do with setting these individual bits and tunnels in this particular way? The answer is, well, they do not have a natural connection between, there's no natural connection between these two, but there's a indirect connection between these two, and that indirect connection is the ROM in the processor. So I'm switching back to the processor design now, and I'm moving this again to the left hand side, and we can probably get more surface area on the main part of this window, because I don't need to change properties anymore, so we can just maximize a little bit more, to see more of the processor like that. Okay, so when we scroll down to the ROM component, we look at this ROM component and go like, we don't see how this has anything to do with what we were talking about. Well, let's go ahead and illustrate this instruction. So at location 00, which is always where the processor starts executing, we'll specify the opcode that we just got, okay? Not the mnemonic. Mnemonic is a symbolic name that you type in an editor, but the opcode is the binary bit pattern, that the processor understands. So the bit pattern has a hexadecimal representation of F9. So I just overtype that location with F9. And in the next location, even though it's not needed, I'm going to specify 01, which is the opcode of halt. So this program will basically just kind of stop going any further. Otherwise, 00 is corresponding to quote-unquote the no op instruction, which just then keeps on going until it wraps around back to F9 again. Okay, but that's not what we wanted to do. So we just injected two instructions over here. So now we have a simple program that is ready to execute. Okay, so now it's time to quote-unquote run this program in the processor. And somebody's going to say, oh, goody, we can just do a Control K and just watch it happen. Well, that's not what we're going to do here. What we'll do is we're going to single clock this entire thing, just so that we understand how the processor executes an instruction. Okay, so this is the part where you might want to revisit later, because I don't want you guys to be taking notes along the way. You can be taking notes along the way if you can follow what I'm saying and taking notes at the same time. But the better a better use of your time and also the daily log document is really just to mark the time and say, okay, it's 9:42 or 9:43-ish, and tech is starting to talk about how instructions execute in the processor, because that gives you a quick and easy way to get back into the video. And so you can watch this part again, and the second time you watch it, because it's not going to be a live session, or if you're watching this as a recording, you can obviously do this too. So if it's not a live session, it gives you the option of pausing, right? You can just pause the whole video. Then you have all the time in the world to jot down your notes in any representation that you want, okay? Using your own words to explain, the key concepts, okay? So this is one part of the class, that I think, some people do not do, but it is really, really important, is to go back to the video and revisit it in a much slower pace. Then you have the time to take your own notes. And I gave you the PDFs too, which makes it easier for you guys to kind of document, and point out which component is doing what, okay? All right, so moving on. So now you cannot see the scroll bar, but the scroll bar is not really important, so that's why I do not put it into the screen part that is being recorded. So we look at this ROM here, and then we ask, what happens when I single clock it right now? We can see the clock is low at this point, it's a 0. So if I do a Control T, which is a single transition of the clock, it's going to go up to a 1. So we have a rising edge. Almost all registers update on the rising edge, with the exception of, the only exception to that rule is the microcode pointer. The microcode pointer is the only one that updates on a falling edge. Okay, so that's the only exception to the rule. So now we ask the question, okay, with a rising edge, what is going to happen to the processor? What's going to happen to all of the registers and things that can update? There are only two things that can update in the processor. One would be all the registers, and the second one is RAM. Okay, so you only have to worry about those two things changing their state when you perform the single clocks. Okay, so this is really important because it really helps you to focus on what component to pay attention to. So what we need to do now is to look at all the registers and ask, okay, is this going to be updated? Is that going to be updated? And so on. And as I said, there are two components that can be updated, upon a rising edge clock. The first one is RAM. So we look at RAM first, okay, and we ask, is this going to be updated on, the next rising edge clock? The answer is no, okay, because when you look at RAM, even though it is selected, we can see RAM cell is a 1, it is being selected. So RAM is paying attention, okay, it's going to do something. But we can also see that RAM load is a 1. So when RAM load is a 1, it means RAM is in a read mode, okay, it's only outputting something from its own content, but it's not updating anything. As long as it's not updating anything, the clock really doesn't mean anything in this operation as far as RAM is concerned, and we also know that RAM is not getting updated. Okay, well, but since it is selected, so that means the data of RAM is kind of important, because you really have to ask the question, if RAM is selected, we are doing something with RAM. But with RAM load is a 1, we know we are reading from RAM. So now the question is what component of the processor is reading location 00 from RAM? And then the second question is, why are we selecting location 00? Who is pointing to location 00? So those are the questions you have to ask whenever RAM is selected. Is 1, do we have a read or write operation? 2, who is specifying the A port? And 3, who is connected to the D port? Okay, so those are the questions to ask whenever you see RAM being selected. So we'll address those questions one by one. We look at the A port first, okay, and then we say who is connected to the A port. Now this part is much easier done in Logisim compared to a PDF, but when you're documenting, okay, in PDF is easier. So we look at this particular node and we see how it connects to the same multiplexer that we looked at earlier. But this time we look at the value of address mux, and the value of address mux is a 1, which means input 1 is now connected to the output for this particular multiplexer. So we have to track down input 1, and we can see input 1 connects to the output of the program counter. So the program counter is specifying where in RAM should I be looking at, at the very beginning of an execution cycle. Okay, and this cycle is also known as the fetch cycle when we talk about the cycles of executing an instruction. So now would be a good time to write down at approximately 9:48 on July 6th. Okay, TAC talked about the fetch cycle of instruction execution. Okay, and then later on you can annotate and document it and use pictures and whatnot. All right, what does that mean? What about the D port? Okay, now we know what connects to the A port of RAM. Now we do ask the second question, which is what connects to the D port? Okay, we are looking at the content of F9 to update something. What is being updated as a result? So now we have to look at all the things that this particular node connects to, and we already know that it connects to one of the things that we looked at earlier. So we look at this and go like, we know this is not an issue, because when you look at this particular enable pin, it is off. Okay, it's dark green, which means this particular demultiplexer is turned off. So if the demultiplexer is turned off, it is not driving any one of its outputs. So as far as the register bank output 0 is concerned, it doesn't connect to the data port at all. Okay, so that's not one of the concerns that we have. So if this is not a concern that we have, let's take a look at this one here. Okay, we know this is not an issue either, because register input enable is also turned off. We can see how this is turned off. And if you right click on the register bank, we can see how this particular input pin connects to the input enable of this particular decoder. And with the enable of a decoder turned off, none of the output of the decoder is going to be a 1, which means none of the registers is paying attention or is going to be updated. So this is not how the data port of RAM is being utilized for. All right, if that is not the case, where else can it go? Oh, I see it can go to this particular multiplexer. So now we scroll down a little bit to see what happens with that particular multiplexer. So with this particular multiplexer, the input is the select is a 0. So this multiplexer is paying attention to the other input, not even this input. So we go like, okay, I guess it's not important then. Okay, so we can stop tracing at this point, because this particular wire is not even used by this multiplexer as the input selected. Then we can also look at things from the perspective of a program counter, from the register perspective. We can see the program counter PC is not enabled because its enable pin is dark green. It is not enabled, which means well, you can present whatever you want to the D port of this particular register, but it's not going to update because it's not enabled. All right, so what other registers do we have? We have the flags register, which is not even remotely connected to the data port at this point. So we go like, okay, that cannot be the issue. So we look at the node, and we finally found that, oh, it also connects to the D port of this instruction register here. And the instruction register does have the enable and being a 1, which means on the next rising edge, okay, when clock goes from 0 to 1, the instruction register is going to be updated. All right. So I know this sounds like a lot of work just to track down what is going to be updated. But when you do this more often, you know where to find the registers, and you will be able to figure out who is going to be updated next just by looking at the enable of the register. Okay, so we click on this wire, and it specifies a content of 1111, 1001. Mine shows F9, yours is going to show a negative number. That's because you can change the radix, or the base, or how the value is represented as a number in Logisim. Let me point out where you can change that. I believe, oops, sorry about that. I believe it is in Preferences. So if you go to Preferences, let me move that window into view. So if you go to Preferences and you go to Window Layout, right there. So when you go to Layout of Preferences, which is under Window, the Window menu, you can go to the bottom part here, which specifies the second radix when wire is poked. The default is signed decimal, and that's why you normally would see a negative number for F9, because the most significant bit, which is the sign bit, is a 1 in this case. But for what we are doing right now, it is much more convenient to look at the value as a in hexadecimal, which is base 16. So that's why I specify hexadecimal in my case. So I would advise you to do the same, because it's a lot easier to kind of track down the value of a wire. Okay, so getting back to this. All right, so we know this register is going to update. In other words, of all this entire discussion, okay, what I can specify in C notation is whatever the instruction register is. I'm just using IR as an abbreviation of the instruction register. It is getting whatever the program counter is pointing to. That is what we call as the fetch cycle. So this is called the fetch cycle. All right. The processor, one component to answer Catherine's question from quite a bit earlier, the answer is only the microcode pointer is updating on the falling edge, but all the other registers and RAM itself would update on a rising edge. All right, so now we Control T, which is a single transition of the clock, like that. Oh, okay, I think I got my pointer in the wrong window. There we go. Try again. Control T. Okay, so now we can see. Okay, let me move that a little bit away. There we go. So we can see how the instruction register is now updated to F9. So what the fetch cycle does is it goes to whatever location in RAM that the program counter is pointing to, and it says, okay, whatever this byte is going to be the opcode of what I'll be executing in this particular execution cycle. Okay, and that the first thing it does is to put it into the instruction register. This is the instruction register. And the next Control T is going to be a falling edge. We know nothing is going to update on the falling edge except for the microcode pointer. The microcode pointer is this guy over here. So, whoops, pointed the wrong thing. This guy over here. So the instruction register, the microcode pointers, okay, kept using the wrong name of the component. The microcode pointer is going to update on the next clock transition. So now we have to ask, how is it going to be updated? The microcode pointer, the input of the register, connects to a multiplexer. So whenever something connects to a multiplexer or the output of the multiplexer, you have to ask which input connects to the register connects to the output. So we can see the select, which is the wire connected to the port that has a little gray dot next to it. This is a 1, which means it is using this to connect to is using this input to connect to the output. So this input goes around to an adder, and the adder always has K0 or carry in as a 1, and it always has Y, which is the other number that we are adding, being a 0. So it's really just incrementing all the time. So if the output of the microcode pointer is 0, then the output of the adder is going to be just 1. Okay, no big deal. And this one is being routed back through the multiplexer back into the input of the microcode pointer. And remember, the microcode pointer updates on the falling edge. So that means when I type Control T on the keyboard for another transition of the clock, the microcode pointer will now increment to 0, 0, 1. Okay, so that's exactly what I'll do now. Control T, and we can see, okay, the microcode pointer is now incremented. But we can also see, because the output of the microcode pointer connects to the A port of ROM, so we can see how location 1 of ROM is now being selected. The ROM is always enabled because the select pin of ROM is always a 1. So now this is what is driving, all these tunnels over here. Okay, if you are to convert 0D80004 into individual bits, okay, and then use the splitters, okay, there are 2 splitters involved over here, and then use the splitters to find out, how, the individual tunnel is getting the zeros and ones. That is what is driving the entire processor, okay? So now we have to go through that whole analysis again, okay? It's basically asking, okay, who's going to be updated this time? So we'll go through that exercise one more time, because I'm your tour guide today. I'm your tour guide to Solar Island, okay? For those of you who remember, that's a reference to Thomas the Tank Engine. If you don't know what is Thomas the Tank Engine and you have time, it's not a bad thing to watch, okay? It's definitely kid friendly. It's not going to be problematic. All right, so once again, we go through all the things that can update, okay, and then ask, is this thing going to be updating, or is it even important in this operation? First thing, look at RAM. And we can see RAM cell is a 0, which means, aha, okay, we are not using RAM in this particular operation. Okay, no big deal. Look at the flags register. It is not being updated. Okay, no problem. In other words, we are trying to find things that are going to be enabled first. So I suggest that you come up with a list of registers so that you have a systematic way of going through all the things that can update in a particular operation of the processor. Okay, I kind of do it without a particular list because I kind of know the processor well enough. But if you're new to this, okay, you probably want to do that. The input enable of the register bank is a 0, so none of the 4 registers A, B, C, or D is going to get updated. Only the program counter is updated. Yeah, actually, yes, okay. But I want to go through the whole thing. So Richard is correct. Register output 0 enable is also a 0, which means none of the register is outputting, but I'm looking for things that are updating. Okay, so let's ignore what I just said. And then we look at the program counter. The program counter has the enable being a 1, so we know that is going to be updated when I type Control T again. So whenever a register is going to be updated, the next natural question is, how is it going to be updated? So the input of the program counter comes from a multiplexer. Whenever the output of a multiplexer is connected, then you have to ask, how is the multiplexer switching the input into the output? That is dictated by the select pin, which is a 0 in this case. So we are looking at input 0. Input 0 comes from, guess what? Another adder. And this adder, once again, has the second number to add being a 0, and then the carry in is a 1. So effectively, we're just adding 1, and that's why you see 0, 1 here. So when I type Control T, the program counter is going to increment from 0, 0 to 0, 1. The instruction register is not being selected, so it's no big deal. And we also know the microcode pointer only updates on the falling edge, and this is a rising edge that we are talking about, so we don't have to worry about the microcode pointer for now. So only the program counter is going to increment in this case. The reason, okay, so this is important. Why are we incrementing the program counter? The reason why we are incrementing the program counter is because we just fetched the opcode. In other words, whatever is at location 00 in RAM is no longer important to me because I got it into the instruction register already. Okay, so to prepare the processor to get to the next instruction, we auto increment the program counter. It is getting the program counter ready to get to the next instruction. That's why we are incrementing the program counter at this point. Okay, so you might want to write this down, okay, when you have time, but we are not gonna, write it down at this point. I'm not going to write it down, but at a later point in time, or if you're typing and you can type really fast, you can just kind of type and go like, the reason why we're incrementing the program counter is because we already got the opcode. We're just setting up for the next instruction to execute. All right, so let's do the actual clock cycle. Control T to give us a rising edge. Okay, so Control T right there, and we can see the program counter is now updated to 0, 1. And now we're going to have a falling edge. Okay, if I type Control T again, we're going to have a falling edge. This part is going to be kind of fun. Okay, because the falling edge is going to update the microcode pointer. We know the microcode pointer is going to be updated every single time because it is enabled all the time. Okay, but what is going to be used to update the microcode pointer? That is the question. So we look at the output of the multiplexer that connects to the input of the microcode pointer, and we see that it's connected to a multiplexer. We look at the select of the multiplexer. It is selecting 0. So we are looking at input 0 of this multiplexer, which goes to something that is really kind of odd, right? This is a splitter or merger. And when we look at this merger, we go, what is that doing? Okay, so we can see how we are using a constant of 0 to specify bit 0 to bit 3 of whatever is going into the merged end of the splitter, and then bit 4 to bit 11 are specified by the tunnel called instruction. The tunnel called instruction is merely just the output of the instruction register. In other words, if I don't mind, having a lot of wires crossing over and whatnot, I could have just connected this wire all the way over to the bottom branch of the splitter. Okay, it would have served exactly the same purpose. So we know this is F9, right? And we know this is 0. So now the question is, how am I combining those two into one single merged end of the splitter? So the least significant 4 bits are constant zeros. The most significant 8 bits, they come straight from the instruction register. So that means the output of the splitter, or in this case, I should call it the merger, is simply F90, because the most significant 2 bits, 1111, 1001, are specified by the instruction register. The least significant 4 bits, 0000, is specified by just the constant of 0, but it's a 4-bit 0. So the result is F90. So F90 is going to be the new value of the microcode pointer. All right, so let me just kind of pause a little bit here so that if you want to jot down a note and say that this is 10:05, and Tech just talked about this is called the decode cycle of executing an instruction. So you might want to jot that down. Okay, this is called the decode cycle of instruction execution. It's called decode because now we look at F9 and go like, I'm using F9 as an index to look into the ROM to find out how the instruction, which is the ST, the store instruction, is actually implemented by configuring all the bits involved. Okay, so I'm looking at Discord and I don't see any questions, and I'm double checking to make sure my Discord is still working because sometimes I see no update and it's because it has crashed. Catherine is typing something. Yeah, it will make more sense, when you rewatch the video, but in slow motion. So then you clear up one concept first before you unpause the video. Then you move on just a little bit further and then slow pause it again. I'm just waiting for both Catherine and Sakio to finish typing. Okay, I'll point out what the big picture is. We are definitely dealing with pine needles at this point, but I'll point out what the tree is and why this tree is important in the forest. And Sakio is typing. I'm gonna wait a little bit for Sakio to finish typing. Okay, so the von Neumann architecture covers this kind of circuit and parts. Well, this is one implementation of a von Neumann architecture, and we can see how the content of RAM is being used to configure the switches in the processor, which then dynamically reroute how the components inside the processor connect to each other. That is the whole idea of the von Neumann architecture, is we are utilizing content of RAM to constantly reconfigure the connections between the components so that the processor can do different things depending on which instruction we're executing. That's kind of so that's a very good question. So RAM is the key part in terms of specifying what we want the processor to do. The ROM, on the other hand, specifies how that something is done. So that's also a very good question. This is also something that you guys might want to write down in your notes. Okay, so very good questions, Sakio. So let me just say that one more time, and you might want to kind of jot down the time mark at this point. Is the RAM specifies what we want to do. Do we want to store? Do we want to load? Do we want to add? Do we want to subtract? Do we want to compare? Do we want to jump? But it doesn't specify how it is done. So the what is being specified and eventually loaded into the instruction register as a buffer. But the instruction register will then get into the microcode pointer, and the microcode pointer is using the instruction register as part of the index into the ROM. The content of the ROM specifies how something is done. It specifies how a load is done, it specifies how a store is done, it specifies how an add is done, and so on. Is that okay? So this is a very good question, Sakio. Very good. Thank you. Because RAM specifies what, the ROM specifies how. Okay, woohoo! All right, so now we are ready to update the microcode pointer to F90, and you can see how the opcode is really just the most significant 2 digits of the location that we're going to go to in ROM, and then the least significant digit in hexadecimal is always a 0. Okay, so let's go ahead and go there. Control T. And woohoo, we are now at location F90, which has a content of 1501882. Okay, so instead of converting all the hexadecimal digits into binary and then figure out which part is which part, the nice thing about having LogicSim is, well, the splitters is already doing that job for us. Okay, so we don't have to manually break it into individual bits. So once again, we look at all those things and ask, who is playing a role in this particular operation? Okay, so now we can see RAM is playing a part because RAM cell is a 1, so it is doing something. So as soon as we see RAM is doing something because the select pin is a 1, then we have the other 3 questions to ask. The second question is, are we reading or writing? So we look at the load pin, and it is a 0. So that means we are writing to RAM. We're updating a RAM location. Then we ask the last 2 questions, the more difficult to answer questions. The first one out of those 2 is, who is specifying the address? And the second part is, who is paying attention to the data port? Well, first thing first, we look at the address port, and we track it down to the multiplexer, and this multiplexer has a select of 0, so we track down input 0, which comes from a demultiplexer, and the output of the demultiplexer is in fact channel output 0, so we now need to look at the input, and it goes into output 1 of the register bank. Then we look into the register bank, okay, and we ask, who is connecting to register output 1? That is dictated by register output 1 select, which is a 0, 1, which means we are connecting input 1 to the output of this multiplexer. So we track that down, and it turns out to be register B. That feels like deja vu, right? I hope so. If you vaguely remember that this is something that we did a little bit earlier today, then you have been paying attention. Good job. Okay? Because that's exactly what we did by manually figuring out how to configure the multiplexers and the demultiplexers so the register B will drive the address port of RAM. Could I rephrase that? Not sure what Sakio is asking me to rephrase. You're asking me to do something that I really cannot do. Not that I'm refusing to do it. Okay, because I cannot remember what I just said. That's the thing. Okay, so let's track this down again. So we know register output 1 is connected to something connected to the address port of RAM outside of the register bank, right? So we now need to say who is connecting to the output of this multiplexer. That is being controlled by the select pin or the select port of the multiplexer, which is the one under the gray dot. So the select port is specified in 01, which means input 01 is connected to the output. This is input 00, this is input 01, this is input 10, and this is input 11. But because it's 01, that means this input connects to the output. That is the whole point of a multiplexer, is to only allow one of the inputs to connect to the output, and the select is selecting which input connects to the output. Yep, that's it. So are we good, Sakio? Okay. So this is what we did last week, was to kind of look into the multiplexer and the demultiplexer, and this is the job of the multiplexer. So now we know that we are connecting the output of register B inside the register bank, and through some demultiplexers and multiplexers, eventually it connects to the address port of RAM. Cool, we got one mystery solved. So now we have to solve the other mystery, which is who is connecting to the data port, right? But if you if you understood why I said, does this feel like deja vu, then you already know how the data port is connected, because we figured this out manually a little bit earlier. But let's go ahead and do this part, okay? So we see the data port connects to a whole bunch of stuff here, okay? But of all the things that it connects to, we also know that the data port is now serving as an input into RAM, which means we're looking for something that is serving as an output, to this particular node at this point. And if you look at all the things that connect to the address to the data port, only this one right here is connected to an output, because the demultiplexer has multiple outputs. So, and the demultiplexer in this case is enabled. Okay. So now we look at the select pin of the demultiplexer, and it is a 10. So this is output 00, this is output 01, this is output 02. So we are in fact connecting the input of this demultiplexer to output 2 of the same multiplexer. So it is important to track down what connects to the input of this demultiplexer. It is output 0 of the register bank. So now we go into the register bank and we ask, okay, register output 0 is this particular output pin. So now we say, what connects the inside of the register bank to this particular output pin? It's going through a multiplexer, and this multiplexer has a select of 10. So now once again we count the inputs. This is input 00, this is input 01, this is input 10. So this is the one that we want. It connects to the output of register C. So I'm guessing that some of you are having that feeling of deja vu again. It's like, oh, isn't that something that we did earlier? You're absolutely right. This is exactly what we did earlier. We did it by hand earlier, but this time it is not done by hand. This time it is the output of the ROM. Okay, so let me go back to the output of the ROM. is the output of the ROM, which is a whole bunch of bits, okay, that eventually specifies the enables, the select of the various components of the processor. In other words, this is why I said a little bit earlier that the content of the ROM specifies how something is done. That is because the ROM is kind of like the conductor of an orchestra. The ROM is now pointing to RAM and say, I want you to pay attention right now, and I want you to get into a mode to update one of your locations, okay? And then it's pointing to some of the multiplexers and demultiplexers and say, I want you guys to be configured like this, so the output 1 of the register bank connects to the A port of RAM. Then it's pointing to a whole bunch of other things inside the register bank and say, I want your output 0, okay, to connect to the D port, okay? And then it goes into the register bank and specify the register B to connect to output 1 and specifies the register C connects to output 0. It is all done by all of these bits coming out of the ROM component. Okay, so now there's probably somebody has a question. It's like, but does this how something is done? Does it really have to be at location F90? The answer is yes and no. Okay, the answer is a yes. Okay, it has to be at location F90 if the opcode that we are specifying is indeed F9, which is in the instruction register. But the answer is no if you are willing to change the opcodes corresponding to the instructions, then it doesn't have to be F9, okay? Because the way I chose F9, which goes back to the browser, let me go switch to the browser at this point, and it is the opcode table that we are talking about here. And let me move this one to the side over here. All right, so why do I choose this particular bit pattern to be the opcode of storing something? It's kind of random, really. I mean, that's really kind of the bottom line is some of these bit patterns is just like me finding, okay, let me find the next block of opcodes, like 16 of them, and find out, so whatever is available, at the time, it's like, okay, let's just choose this one. It is somewhat random, okay? But once I have chosen the opcode, then I have no choice but to use, okay, this is not what I want. Let me close this. So once I have chosen the opcode in the opcode table, then I have to be consistent. Okay, this is also the wrong window. Sorry about that. Let me close that. And this is the correct one. Okay, so once I have chosen F9 as the opcode, then the how, okay, the bit pattern that specifies all the select, all the enable, of the components inside the processor, that particular bit pattern now has to reside at location F90 in ROM. Okay, so that is the connection between opcode and the content of ROM. Now, one location of ROM, which is, in this case 1501882, sometimes I call it a slice, okay? In fact, a slice of time. In other words, a slice in ROM is one step to implement a particular operation that we specify as mnemonic, which then turns into opcode by the assembler. Okay, Catherine is typing something. I'm gonna wait for that question. So is that the info stored in ROM at location F90? That is correct. Okay, so the content at location F90 is in hexadecimal 1501A82. That is correct. So this is the location or the address, and this is the content at that location in ROM. All right. So we want to see, whether this bit pattern, the long bit pattern of 1501A82 is in fact going to store whatever register C has to the location that register B is pointing to. So the next Control T should show us that. But I'm going to wait until Martin is done typing. And the current time is about 10:22:53, just so that people who watch the video can go back to the Discord chat channel. So Martin is asking, so is the ROM content what is tied to your opcode table for the assembler language? Yes. So the ROM content, has to be consistent with the assembler, because the assembler is translating the mnemonic into opcode, but there has to be a consistency between the opcode and the content of ROM, because the content of ROM is eventually what specifies how something is done, and then the opcode is only specifying what needs to be done, but without actually knowing the bit pattern to specify to all of the multiplexers, demultiplexers, registers, and RAM. So are we good so far? All right. So I'm assuming that we are still doing okay. So now what we'll do is we are going to focus on RAM, because now we know exactly what connects to the A port. It's coming out of register B, and we also know what specifies port D, which is coming out of register C. So this is from register B, this is from register B, this is from register C. Oh, sure, you're welcome. So now we're ready to do another Control T, to have a rising edge, because this rising edge is going to update the RAM. Okay, so Control T right there, and we can see how location C 4, 5, 6, 7, so how C7, location C7 is updated to the content of 6E. So that's exactly what we wanted to do. Woohoo! So that completes the explanation, almost completing the explanation of one instruction, but we got just a little bit more to go. I know we are already kind of over the lecture time, but I got to finish this. Okay, so the next question to ask is, now we're going to have a falling edge of the clock, and we know the micro code pointer, okay, which is seen as U code pointer, is going to update. So how is it going to be updated this time? The select of this multiplexer is now a 1, which means we're just incrementing. So we would go to location F91, right? So if I Control T, we should see the ROM selecting location F91, and then we'll decode that bit pattern and figure out what it's going to do. Unfortunately, that is not what's going to happen, or at least apparently that is not what's going to happen. So I'm going to do a Control T here, and just keep your eyes on the ROM and see what happens. Control T now. Whoa, what just happened here? Why are we back to location 0, 0, 0? So what we need to do is go to location F91 and just take a look at what is there. Okay, I'm going to move the window over, so give me a little bit of time to move it. Okay, here we go. Okay, so this is the content of ROM, and kind of in a way that we can easily go to a particular location. F91 is where we need to go. So this is F90 and this is F91, and you can see F91 doesn't look too suspicious. I mean, it's just 2 followed by a whole bunch of zeros. So it is 2 followed by 6 zeros in hexadecimal. 1 hexadecimal is 4 bits, so 6 times 4 is 24. Okay, bit 25 would specify a 1 in the most significant digit, and bit 24 is going to specify a 1 in the most significant digit, and bit 25 is going to specify this 2 as the most significant digit in hexadecimal. So this 2 followed by 6 zeros is really just specifying bit 25 being a 1 and everything else being zeros. Okay, let's close this window and see what happens. What is bit 25 connected to? This is bit 25, okay, out of the ROM. It's going through a OR gate, okay? And the other input is the reset, but it's going through an OR gate. And guess where it connects to? It connects to the reset of the microcode pointer. So that means at that very brief moment, okay, that ROM location F91 is in fact selected, the output of that location causes the reset of the microcode pointer, which then makes the microcode pointer to go back to location 000, which is going back to, guess what? The fetch cycle. So this is how we get to the next instruction, okay? So at the end of each of the microcode slices of each instruction is that 2 followed by 6 0 pattern, which forces the microcode pointer to go back to location 000, which starts the next fetch cycle, the fetch cycle of the next instruction. So this is how we got to the next location, and then the next location, and then the next location. So this time it is the program counter is telling us where we need to go to get the next opcode, and we kind of know, what is at location 01 already because I put in a 01 at location 01, and the opcode 01 is corresponding to the halt instruction. So I'll just kind of quickly get to the ROM location. So I'm doing Control T a few times really kind of quickly this time. So this is it will increment the program counter. Now we are decoding, okay? So when we're done decoding, we get to location 010, okay? That's not surprising because 01 is the opcode and 010 is the location in ROM that starts the quote-unquote implementation or the how of that particular instruction. And we got all zeros here, okay? So what is that going to do? You probably already guessed what it's going to do. Absolutely nothing, because we know that none of the registers is enabled, because in order for a register to be enabled, something has to be a 1, okay? We know the RAM is not selected, because in order for RAM cell, which is coming out of the ROM, to be a 1, one of these digits in hexadecimal cannot be a 0, okay? So we know nothing is being selected, nothing is getting updated, okay? Okay, so if nothing is going to be updated, what about the ROM itself? Okay, in other words, the ROM itself, still needs to go up by 1 location, right? It means still has to go to the next place to go. So let's see what's going to happen in the rising edge. We know is not an issue because none of the things that can update on the rising edge is enabled. Okay, the RAM is not enabled. None of the 4 registers A, B, C, or D is enabled. The program counter is not enabled. The flag register is not enabled. The instruction register is not enabled. None of them is paying attention at all. They're all daydreaming. Your entire orchestra is falling asleep. Nobody is holding on to a musical instrument. Okay, there's no sound coming out of this orchestra on the rising edge. Okay, but we know with the falling edge, the register called microcode pointer is always selected. It's always doing something, right? So let's find out what this thing is going to do. So the microcode pointer is enabled, and the input of the microcode pointer is connected through a multiplexer to input 0. Wait, hold on a second here. Didn't we just do that a little bit earlier? Yes, we did. Okay, so it's coming from the instruction register again, which means we're going to go back to location 010 on the falling edge. Okay, so if I type Control T at this point on the keyboard, it's a rising edge, and I type it again, it's a falling edge. Normally, when we have a falling edge on the microcode pointer, something happens in ROM. Okay, where we select on in ROM is going to change. Not this time, because this time the input into the microcode pointer is 010, and it is the same as its current output. In other words, there's absolutely no change to the microcode pointer itself. If the microcode pointer itself is not being changed, then the rest of the processor is not going to update anything. Okay, so we do Control T again, and we can do Control T as many times as we want, and we can see that absolutely nothing happens at this point. And that's because we are now at a halt state of the processor, which means we're done. Okay, we don't have anything further to do. That's what halt really means when it comes to a processor. We can also see there's an output pin, with the name of halt, and that is an indication that we have reached, quote unquote, the end of the execution of a program, is when we see a 1, at the output pin of halt. Okay, so that completes the execution of this really kind of rather simple program. When you do the lab today, you're going to have to deal with load. Okay, so the first thing you need to do is to go to the opcode table to find out what the load instruction is supposed to do. And there's the other one is LDI, which is a little bit more awkward, but it's I think you guys can do it too. So this is LDI, which is load immediate. This I here, instead of Y, it has an I means it has to be a constant. Okay, give it a decimal number. Okay, that's what I it needs to be. But it can also be a label. But the concept of a label is also introduced in today's lab. So today's lab is not really just okay, let's do all these steps to reinforce the concept, but it also has concepts on its own. So it's really kind of important to take it slow with the lab, jot down some notes if you want to as you go through the steps in the lab. So this is LDI and this is LD. The difference is with LDI, you are just initializing a register which is specified by the placeholder X to a particular constant. Okay, I want register A to now have a value of 2. Then you do a LDI A, 2. With LD, it is the reverse of ST. Okay, so the load instruction is updating a register based on the content of a location in RAM that possibly another register points to. X and Y do not have to be different registers. They can be the same register. So if you say LD A and then in parentheses A, then you are using register A first to specify which location in RAM. Then you use the content at that location to update register A itself. So you can use the same register in both the placeholder X and Y with the LD instruction. Okay, so that pretty much finishes today's lecture. And once again, today's lab is going to be a little bit more time consuming because you're going to have to go through more or less the same exercise that I just went through with the ST instruction, but you would do that to the LD and the LDI instruction, because that is how you can gain the most insight into how instructions execute and how they're implemented in this particular processor. Whew. Okay, so there's a lot of material in today's class. So once again, use the recording because that really is going to be one of the best resources is to listen to the lecture again and pause it. Now, if you get to a certain point of the video and you have thought about it, you listen to it a little bit more, and you still cannot figure out what I meant when I said something, then it's time to ask me in Discord. Okay, so don't hesitate to ask, but try to kind of slow down and understand the concepts on your own first. But if you absolutely cannot figure it out, okay, then you should ask me. All right, so that's the end of today's lecture. I will take a 10-minute break and then I'll be back at 10:37. So I'll just write down here. Oh, okay. Well, you are welcome. Oh, 10:47, not 37. There we go.